Hello, my Calc 2 students. Today we talk about Taylor and Maclaurin series. This is section 9.10. 9.10. It's last section for this class. Series we call Taylor series for function fx. Series when you have n change from 0 to infinity, nth order derivative, value at point C, divided by n factorial, x minus c, n power. You see it's similar with your Taylor polynomial, but Taylor polynomial has some constant degree. Here we have infinity. And if c equals 0, you have Maclaurin series. It will be n from 0 to infinity, value your derivative for point 0 over n factorial and x power n. Doing some example. Example A. Let's go. Our function fx is sine x, and we try build Maclaurin series for this function. First derivative will be cosine x. Second derivative will be negative sine x. Third derivative will be negative cosine x. And fourth derivative will be sine x. This means you have like cycle, and fifth derivative will be cosine, sixth will be negative sine, then negative cosine, then again sine, and continue. This means we have some pattern here. If x equals 0, value you have 0, 1, 0, negative 1, 0. And now we're ready for write our series. It will be 1, this means here I have x, then I have third derivative non-zeros, this means I have minus 1 over 3 factorial x to the third. Then as next non-zero, it will be fifth derivative. It will be plus 1. Plus 1 over 5 factorial x to the fifth degree. Next non-zero, it will be seventh derivative, minus 1 x to the 7. And you can continue, and you have plus 1 over 9 factorial x to the 9, and continue. This will be Maclaurin polynomial for function sine x. And now we have some theorem, but before we remember what was arrow here. We have formula when we use Maclaurin and Taylor polynomial. Arrow was this n plus first derivative for some point zeta over n plus 1 factorial times x minus c n plus 1 power. And our theorem tells us, this is remember definition, and our theorem tells us if limit Rn for n approach to infinity equals 0 for all x from some interval I, then Taylor series converges and equivalent your function fx. Okay. Doing example B, we have here gx equal sine from x squared. We can try found derivative. It will be 2x cosine x squared. Then found second derivative. It will be, now it's like product. It will be 2 cosine x squared minus 4x sine x squared, and doing all. Or I think it's much easier if you remember sine x we built right now. It will be x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the fifth minus 7 factorial x to the seventh, and continue. And what will be sine x squared? We only switch from x to x squared, and you have x squared minus 1 over 3 factorial x squared to the third degree plus 1 over 5 factorial x squared to the fifth degree to the seventh degree, and continue. It will be x squared minus 1 over 3 factorial x to the sixth plus 1 over 5 factorial x to the 10th minus over 7 factorial x to 14, and continue. Okay. Now we study one more type of series. It's called binomial series. Let's go. We have function fx is 1 plus x to the power k. Try found couple of derivatives here. First derivative will be k 1 plus x power k minus 1. Second derivative, it will be k times k minus 1 plus x k minus 2. And this means nth derivative, it will be k minus 1, and continue until k minus n plus 1 plus x power k minus n. Use this fact, we try build our polynomial. It will be Maclaurin polynomial, because if you plug in x equal 0 here, you have, because we don't have space here. Okay, if I'm not sure it's help us. Okay, maybe I'm doing f from 0, it will be 1. F prime from 0, it will be k. Second derivative from 0, it will be k times k minus 1. And an order derivative from 0, it will be product k minus 1, continue k minus n plus 1. Okay. Use this fact. We built our Maclaurin series. It will be, okay, for our function 1 plus x to the power k, it will be 1 plus kx plus k times k minus 1 over 2x squared plus, and terms will be k times k minus 1, k minus n plus 1 over n factorial, and here we have x to the power n. Continue. Okay, this binomial series help us write like Maclaurin series, for example, for a couple of functions. Well, example number C, example C. Okay, fx, let's go, it will be cube root from 1 plus x. This is k equal 1/3. And this means 1 plus x to 1/3 power, it will be 1 plus 1/3 x minus, here we need k multiplied by k minus 1, this means 1/3 minus 2/3, and it's give us 2 over 3 square, then 2 factorial here and x square. Next term will be plus 2 times 5, here we have 3 third degree, 3 factorial, and this will be x to the cube, and you can continue if you want. In book, page 670, you have table for Maclaurin or Taylor polynomial. It depends what kind of function you have here. And very useful table, and we can use in the when we're solving problems. Okay. Question number 4. Here you have your function is sine x. You need build a Taylor polynomial if c equal pi over 4. Derivative, it will be cosine. Second derivative, it will be minus sine. Third derivative, it will be minus cosine. And fourth derivative, it will be sine. This means next this will be for like cycle continue replay. Okay, plugging pi over 4, we have sine pi over 4 square root of 2 over 2, cosine square root of 2 over 2, minus square root of 2 over 2, minus square root of 2 over 2, then square root of 2 over 2. This means you always have same number, but first, second positive, third, fourth negative, then 2 positive, 2 negative, 2 positive, 2 negative. Okay, what we have? This means our polynomial, it will be square root of 2 over 2 plus square root of 2 over 2 x minus pi over 4. Then we have minus square root of 2 over 2 times 2 factorial x minus pi over 4 square. then minus square root of 2 over 2 times 3 factorial x minus pi over 4 third degree plus square root of 2 over 2 4 factorial, it will be square root of 2 over 2, okay, x minus pi over 4 fourth degree, and continue. Next, number 6. They ask us found Taylor polynomial for function 1 over 1 minus x at c equal to. Well, I think we don't need doing. We can do it without any derivative. You're only doing alt trick. We write like 1 minus. I need center 2. This means I write x minus 2. But if I'm distribute, this means I'm add 2. I need subtract 2. Okay, here I have 1 minus 1 minus x minus 2. Because 1 is need be always here as positive, this means here I have minus 1 over 1 minus negative x minus 2, and it will be series. We can write minus here, negative 1 power n x minus 2 power n, and start with 0 to infinity. It will be series negative 1 power n plus 1 x minus 2 power n, and start with 0 to infinity. This means not always you need found all derivative. Okay. Number 16. Here you have function fx with hyperbolic cosine x, and then you need proof Maclaurin series for this function converges for all x. This means interval converging, negative infinity, positive infinity. Okay, great. First we build our function. Well, first we remember what is it. Fx is e exponent x plus e exponent minus x over 2. This is definition our hyperbolic cosine. E exponent x, you can take it from table. It will be 1 plus x plus, or we build couple of times 2 factorial. We build not series, we build polynomial, but you can easily see how it's happened to its series. 3 factorial plus 4 factorial plus continue x to the n over n factorial, and this will be it. I'm specially write this way because what happens is if you have e to the negative x power, this means I need plugging minus x, then we have x before. Okay, it will be 1 minus x, then it's minus x squared, it gives us x squared. This means here I have x squared over 2 factorial. Because it's third degree, it gives us minus x cubed over 3 factorial. Because it's even, it will be plus. And this, I don't know what is depend x, depend n, I have something like this. If we add these two series, what you have? You have e to the x plus e to the negative x power, it will be 2 plus twice x squared over 2 factorial plus twice x4 over 4 factorial, and plus all is even. This means if we divide by hyperbolic cosine x, it means we need take it 1/2, and finally it will be 1 plus x squared over 2 factorial plus x fourth over 4 factorial. This means we have x to the power 2n over 2n factorial, whereas n change from 0 to infinity. Okay? Now about interval convergence. We use our ratio test and we have limit and approach to infinity x to the twice n plus 1 over twice n plus 1, it's an plus 1 terms, and divide by n terms. This means here's factorial 2n factorial over x to the power 2n. Okay, we have x squared limit. Here we have 1 over 2n plus 1, and next term it will be 2n plus 2, and approach to infinity. This limit is equals 0. This means our series converges for all x, or for any x from interval negative infinity, infinity. And now solving, for example, number 26, oops, 26, not 28. Here we need to use binomial series for writing function fx is square root from 1 plus x squared. Okay. First we, x cube. Okay, x cube. First, build some function gx equal square root from 1 plus x. What we have here? Binomial series give us 1 plus 1/2 x plus 1/2 times 1/2 minus 1 over 2 factorial x squared, then plus 1/2 minus 1, then we have 1/2 minus 2 over 3 factorial x to the cube, and continue. This means we have 1 plus half of x minus 1/4 times 2 factorial x squared. Here it will be for negative 3/2, and it will be positive 3/8. This means plus 3/8 factorial x to the third. Okay, and next terms you can count it, but this is function of square root from 1 plus x. What happened if you have square root from 1 plus x cubed? This means you need switch x for x to the third degree. And for function fx, our binomial series will be 1 plus 1 half x to the third minus 1 over 4 times 2 factorial x to the third square, it will be x to the 6 plus 3 over 8 times 3 factorial x to the 9th, and you can continue. This will be final answer. Okay. Oop. Next question. I want to show you number 39 because what is interesting here? Here you have fx equal cosine square x. Yes, right, you can remember or see Maclaurin polynomial. Here is asked us build Maclaurin polynomial for function cosine x, and it will be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial, and then continue. And then because they ask us cosine squared, then you square it, and I'm not sure, you can do it, but I'm not sure it will be very simple. But because we have cosine square x, you can remember cosine square x is 1 plus cosine 2x over 2, right? And this mean is it will be 1 half plus 1 half cosine 2x. A cosine 2x build is no problem. We only for our given Maclaurin series we switch for 2x, and what we have 1 minus 2 square x squared over 2 factorial plus 2 fourths x fourths over 4 factorial minus 2 6 x 6 over 6 factorial, and continue. This means cosine square x will be 1 half plus 1 half from this one is 1 minus 2 square x squared over 2 factorial plus 2 fourths x fourths over 4 factorial, and continue. Distribute and open. You have 1, then you have, okay, this will be minus 2x squared over 2 factorial plus 2 to the third degree x to the 4th over 4 factorial. This means next one will be minus 2 to the 5th x to the 6 over 6 factorial, and continue. You can easily write. Okay. One more question, and I want to show you 44. It will be, if your function is piecewise function equal arc sine x over x for any x except 0, and equal 1 if x equals 0. Here we take it, and we need build Maclaurin polynomial for this series, for this function, Maclaurin series for this function. Arc sine x plus x cubed 2 times 3 plus 1 times 3 times x to the 5th degree over 2, 4, 5 plus 1 times 3 times 5 x to the 7th degrees over 2, 4, 6, 7. Okay, here I'm all take it in from table. You don't need to remember. What will be arc sine? Arc sine x over x. We only divide by x each term, and we have 1 plus x squared over 2 times 3 plus 1 times 3 x to the 4th over 2 times 4 times 5 plus, it's in there, oh no, plus is next term, sorry, 1 times 3 times 5 x to the 6 over 2 times 4 times 6 times 7, and you can continue. And what is interesting, if you plug in for this series x equals 0, you have exactly 1. This means it's work for this kind of function. Okay, I think I need to show you one more example. I found from book how we can use our function for evaluating our series. Just a moment. I forgot about this kind of question, but I'm absolutely sure I need to show you this question. Sorry, it's taken longer. Okay. Okay. Here you have for example, something like this. You need evaluate series 2 power n over n factorial, whereas n from 0 to infinity. And question evaluate this sum. This means found what is this series exactly equal. Okay. I'm found something x to the power n over n factorial and change from 0 to infinity. If you look in here, it will be exactly e to the power x. Use this fact, we can go back, and our series will be e to the square, because it's value if x is equal to e to the square. Use calculator and counting, or e to the square, it's good enough. It's it for today, for this section. Okay.